So we'll do filter design, and this one is by the pole zero placement method. And just to start the whole process, I thought it wise to put just a few points that you might have already heard that when a zero is placed at a point on the z plane, the frequency response will be zero there. A pole, on the other hand, will causes a peak at that point, right? And poles which are closer to the unit circles give large peaks, whereas zeros which are close to or even on the unit circles give um, the trough or the minima. Okay, so in a sense, when you strategically place poles and zeros, you can build a filter, and that's what this whole procedure of pole zero placement is about. So what you see here is called a z-plane, right? You've seen it a lot of time doing z transforms, but probably um, might have forget, but it's not anything new. So it's the z-plane, and we use unit circles to judge the whole uh, pole zero placement on the z-plane. Okay, so this circle you see here, it has a radius of 1, right? That's the maximum radius of 1, right? And any point which falls on it is said to be on the unit circle. It's called the unit circle because it has a radius of 1. Now, the variation of the sampling frequency, right, with the unit circle is also shown by this graph. So you realize that when the sampling frequency is at 0, right, you have a pole placed on the x-axis of the unit circle, and there are other multiples of the sampling frequency. But for now, we'll just take a question, right? How it's going to be presented to you to solve the whole process. So, for example, you have to illustrate the simple pole zero method of calculating the filter coefficients of a bandpass digital filter to meet the following requirement specifications. Okay, now the filter in question is supposed to have complete signal rejection at what DC and at 250 hertz. Now you already know what a bandpass filter is. The bandpass filter is just a filter that it has just let's say a band, right? So let's say the range of frequencies here. So let's say we are starting from frequency 0, let's say to 10 hertz, 20 hertz, let's say at 30 hertz to maybe 60 hertz, right? That is when only the filter will not attenuate the signal. Attenuate means that to make the signal 0. Okay, so apart from that, it would apart from between 30 and 60 hertz, it will make the signal 0. That's basically a bandpass filter. uh, those are in other materials, but yes, that's in a bandpass filter. Now we are looking for complete DC rejection at complete signal rejection. That's we want complete attenuation at DC and at 250 hertz, right? And a narrow bandpass which is centered at 125 hertz and a 3 dB bandwidth of 10 hertz, right? So the requirements are, should I say, a bit stringent, but let's see. It means that the filter should have roughly a characteristics like this. So if we are drawing this showing the x-axis as our frequency, okay, so at 0 we shouldn't have a signal. So at 0 the filter signal should be 0. Okay, now we should have a narrow bandpass centered at 125 hertz. So it means that there should be a center, right, at 125 hertz, right, where our band pass is going to be centered. Then we should have a 3 dB frequency of 10 hertz, right? The 3 dB frequency is actually more or less the frequencies at which, when you see, the filters are not ideal, okay? So when we are judging the filter quality, we usually use what we call the 3 dB bandwidth, right? And above the 3 dB bandwidth, the filter will be attenuated by more than half of its power, right? That's the whole judgment procedure. Okay, so this filter should have a 3 dB bandwidth, right? They set bandwidth at what? Of 10 hertz, right? So it means that between 125, behind it of 120 hertz, and in front of it is what? 130 hertz. Like, a bandwidth of 10 hertz means that there is 5 hertz on the right and 5 hertz on the left. Okay, so we are basically looking for a filter which has kind of these characteristics. Okay, between 120 and 130 hertz, it would allow the signal to pass. Elsewhere, it would attenuate the signal. Now, it's yes, but that's a whole lot of explanation. Let's get sub into the question. Now, one thing you should also really note about this whole procedure is your sampling frequency. Okay, you realize that your sampling frequency determines how your frequency domain design wraps around the unit circle. Kind of, okay. So you realize that there were multiples of the sampling frequency and how to wrap around the unit circle. Okay, yes. Um, that's for another day, but for now, let's explain this. So you had a sampling frequency of 500 hertz, right? Now you are asked to solve it, right? So you can realize that since complete rejection is required at 0 hertz and 250 hertz, right? We need to place poles at those points. Okay. Now, anytime you are designing a filter and it's for the real world, right? Usually think in the direction of pairs of poles and pairs of zeros, like if there is that, because you see these transforms, the z transforms, yes, especially which we are using here, so the z transform has components both in the imaginary and the real component. Okay, so you remember something like z is equal to u is the power I and omega, right? Something like that. You realize that this I is the imaginary component. Okay, and we can't really design for imaginary components when we are dealing with a real world system. Okay, so anytime you start thinking about a filter, start thinking about pairs. Now, you were fortunate that you were told the pairs for the zeros, and for the zeros, right? The pairs were 0, right, at frequency 0 and at frequency 250. So you have to work on them. So at frequency 0, right, when you are trying to place frequency 0 on the unit circle, frequency our angles on the unit circle. Remember, I told you that your sampling frequency is more or less how your frequencies wrap around the z unit circle. Okay, so first we were given that it is required at 0 and 250. That is the signal rejection. So in calculating the zero, the first one will be 0 over what is the sampling frequency. We were told that it was 500 hertz, so 500 times we are dealing with a circle, so the total angle is 360. This one will give you 0, right? So we know that one of the pole has an angle of 0. Okay, fine, we'll keep this in head. And the second one was what, at 250, right? So 250 over 500 times 360. Okay, now this will give you 180. Okay, 180 degrees. So realize that if we are to visualize this on a circle, realize that one will be at 0 and one will be at 180, like depending on how you measure your circle, right? But the major important part is that these things are on the real axis. You see, in the z plane or in the z diagram, remember that this one is imaginary, right? And this one is real. Okay, yes. So if we are getting poles on the real axis, it's very plausible for real world design. Okay, and that is what we want to see. Now, the filter is supposed to have a pass band. You see, the signal rejection was for the zeros. The pass band is for the poles, because that is where the response is supposed to allow the signal to pass or go high. The zeros are where the signals are like attenuated, they are at the ground. Okay, so we also calculate for that, and in evaluating for that, the procedure doesn't change. Okay, so we have a narrow pass band at what, 125 Hz. So let's calculate 125 over 500, the sampling frequency, times 360, right? This gives you 90 degrees. Now this time around, you're unfortunate. When we plot 90 degrees on the, assuming we are starting 0 degrees from here, on the z plane, you realize that 90 degrees will be somewhere here. Okay, now 90 degrees is imaginary, but we are dealing with real world filter design. Okay, so it means that it has to, the poles and zeros have to come in complement pairs. Now we did not need to complement our zeros because they were all real, right? 0 degrees fell on the x-axis, 180 degrees also fell on the x-axis, but it didn't happen so for our poles. Okay, so it means that our poles, the angle for our poles will be what, plus or minus 90 degrees, because one occurred at it occurred at positive 90 degrees, right? But we want our coefficients to be real. Okay, maybe you don't understand why this coefficient to be real thing, but do you remember this in um what the complex numbers? That you remember this in complex numbers, that when you add e raised to the power I theta, now see, e raised to the power I theta has a positive angle, right? Now when I add it to e raised to the power minus I theta, right, what do I get? i'll get I'll get cosine of theta. Do you remember this? I mean, let's expand. Probably you've forgotten. So e raised to the power I theta is the same as cos theta plus I sine theta, right? And e raised to the power minus I theta is the same as cos of minus theta, which is the same as cos theta, right? But sine of minus theta is the same as minus what, sine theta. So we get minus I sine theta, right? Now it rings bells. So yes, this is supposed to give you 2. So you realize that here will give you what, cos theta plus cos theta. Then this sign will cancel this sign. Okay. Yes, so that is how we get positive, okay, from the addition of the imaginary numbers. Okay, and that's our whole idea. Our whole idea is that if one angle is positive and the other is negative, they will cancel out to give us a real number. We want a real number because we are designing a real system. Okay, so far so good. We've been able to get our poles and our zeros. Now once you attain that, your whole design process is done, right? All you need to do is to write it in a very plausible form. Okay, by plausible I mean you had the whole point is you have to have z times okay, let me call the the zeros. So z, let me call the zeros a. So you have z minus a1 times z minus a2, all the way, like you have multiples of zeros multiplying at the top, and you also have multiples of poles multiplying at the bottom. I mean, you probably seen this formula before. Okay, so that's the same way we are coming to put it. Okay, we are coming to represent this in terms of zeros and poles, right? But before, one thing about the Z diagram is you have to also remember that it's a unit circle, right? But zeros are placed on the unit circle because at that point the function is supposed to be completely attenuated. You remember that one from the very first reading. But poles are supposed to be placed inside the unit circle. Okay, now the closer they are placed to the unit circle, the more they approach infinity for the poles. And the further away they are placed on the unit circle, the less they approach like a maxima, right? So that's what we are coming to do. Now it means that we have to evaluate our radius. Okay, from our previous calculations or the observation we made that the zeros are supposed to be on the unit circle, we can see that the radius for the zeros is 1, like they will be on the unit circle, right? So there is no need to bother, their radius will be 1. So when you draw the unit circle, right, we are told that the radius here is 1, right, and the zeros will lie on the unit circle, right? The poles ideally should lie in the unit circle, so they are the ones which have hectic characteristics in terms of calculating for their radii. So to calculate for the radius of the poles, right, there is a formula. It's a more or less approximation, right? So the radius of the pole is given as 1 minus, right, the bandwidth of the signal over the sampling frequency times pi. Okay, so 1 minus, what was the bandwidth of the signal? You were told that the bandwidth is what, 10 hertz. So 10 over, what was the sampling frequency? I think it was 500 times pi. Okay, now I think when you point this in your calculator, I get something like 0.937. Now this is the radius for the poles, not the zeros. Okay, because the zeros will lie on the unit circle. So that gives you the advantage of solving for now you can now write your equation, right? So in writing your equation, like I said, it will be zeros, z minus the zeros, right? I don't want to use z to represent the zero again, so I have to use a z minus a2 continuously. We also have the denominator z minus p1, z minus p2, I mean continuously. Remember that generally the transfer function should look like this. So in that case, then we have to start writing. Now our poles are 2, our zeros are 2. So one of our zeros, right, occurred at an angle of 0 degrees. Okay, now if you are to represent this in the Euler's formula form, remember that the Euler's formula represents any imaginary number, right, as r e raised to the power I theta. Hope you remember that. Okay, now this is a 0, so the r is 1. Okay, so at 0 degrees our component, or our 0 component, will be what? 1 multiplying e raised to the power I. What is theta? Theta is 0 degrees. Okay, yes, theta is the angle, right? So I mean that e raised to the power, so it will be 1 times e raised to the power 0, because 0 times I is 0, and this gives us what? 1, right? So one of our 0 components is 1. Now another of our 0 components occurs at 180. Okay, so we have to write it. Now when we write it, realize that we get 1 e raised to the power I. What is theta? Theta is 180 degrees. Fine, we can put the 180 degrees here, but I mean 180 degrees is the same as I think pi. Okay, so we can put pi here. All right, yes, and now we can represent this in terms of a complex number. Okay, so this is the same as what? Cosine of pi plus I sine of pi. Okay, and I think cosine of pi is -1, right? Sine of pi is 0. So it means that for 180 degrees, our 0 will be at what? -1. Okay, so we have 1 and -1. So for the numerator of our expression, we'll have z minus 1, right? For this one, z minus the pole value times z minus -1. So it will be what? Z plus 1. Okay, for our numerator. We go to the same iteration for our denominator, and it really doesn't change. Okay, I even think I should leave it for you, but let's still go through it. So for our denominator of the expression, we know our r, we calculated it. Remember that this is a pole. Pole usually lie in the unit circle, and we calculated our pole as what? 0.937 from the calculation. Okay, so the when we are trying to represent it in the Euler's format, r e raised to the power I theta. For the very first pole, which we are seeing occurs at positive 90 degrees, right? So at positive 90 degrees. So for the positive 90 degrees one, right, it will be what? 0.937 e raised to the power I theta, right? But instead of putting theta here, I mean 90 degrees is the same as pi over 2. Okay, so that we don't write plenty. Then you now express this in um should I say long form? Okay, or you can even leave it like this for now so that I use it in the calculation later. Now at minus 90 degrees, so at minus 90 degrees, this same expression will occur at what? 0.937 e raised to the power minus I pi on 2. All right, yes, because this is minus 90 degrees. Okay, so then we can come and put it here as our denominator. So this is our numerator, and our denominator will occur out z minus 0.937 e raised to the power I pi on 2, then 0.937. Let me clean the side so that 0.937, no, sorry, it's supposed to be z first. So z minus 0.937 e raised to the power minus I pi on 2. Okay, so something like that. Then you can go ahead and simplify. Okay, you can simplify the numerator, you can simplify the denominator, but I mean you can already see some few simplifications when you try expanding. You can realize that in the numerator it will be just z squared minus 1. I mean difference of 2 squared over the denominator will be a bit hectic, but remember that we are dealing with pi over 2, right? And pi over 2 is a special angle. I mean cos of pi over 2 is 0, cos 90 is 0. Okay, so it means that here can just be written as z minus 0.937 sine of pi on 2. Right, now this expression will have I attached to it because sine is imaginary, right? Then on the other end, we'll have to deal with z plus, because remember we'll be dealing with what? Sine of minus pi over 2, so the negative would come and cancel. We shouldn't go through the whole process of elimination now. So we get what? 0.937 sine pi over 2. Okay, remember sine of minus pi is the same as minus sine of pi. Then we can go ahead and simplify. So I think for the simplification process, I can leave it to you. You can go ahead, simplify. Remember here, I is attached to this as well. Those are the sign components. So at the end of the day, you should get a denominator with real components only, um, no, how do you call it? No imaginary components. Yes, so the numerator you get this one. At the denominator, after you have expanded, you should get something like this one. Okay. Now, once you get these two, the procedure is to express it in the standard format for a filter difference equation. And this is the standard format. You should have a constant one here, right? At the denominator. You don't really care what happens in the numerator, but you should have a constant one there, right? So since we have a constant one here, okay, since we have z squared minus 1 all over z squared plus 0.877669, and mind you, make sure you have a lot of decimal places so that your filter would not be erroneous because of approximation errors. Okay, so yes, have a lot of decimal places like you see here. So they just divided the numerator and the denominator by z squared, right? And when you do that, you arrive at this one, right? That's that's understandable now. So obviously at this point, if you can remember the formula for our general zero pole placement method equation, right, that we use to write our difference equation, right, it's helpful. So remember the formula looks basically like this, right? Summation of a n's raised to the power summation of a n's multiplying z raised to the power minus n all over 1 minus some b n's raised to the power minus b of n, minus b of n. Now these are just the filter coefficients. Okay, so all you have to do is you just have to watch the powers of the ANs and BNs and be writing them. Okay, but take note, here is negative so that you don't make the mistake, right? So your equation can just be y of n, right? Because yes, I mean it's on the left hand side, that's what starts y of n, right? And when you watch this equation carefully, let me clean here, you realize that you have positive 0.877, right, but it's at the denominator and it's a type of b. Okay, because it's at the denominator, remember here is negative but here is positive, right? So it means that you have to put a negative answer here. Okay, so it has to be what, minus 0.877969, and you check what is the power of z attached. The power of z attached is what, minus 2, so it has to be what, y of what, n minus 2, right, plus, so we are done with the zeros, we are done with the poles. Okay, because here's 1, here's 1, so that one has been dealt it. Here was just one term, so that one term has been dealt it. Plus, then let's continue to add the zeros. Well, the zeros at the top, we have 1. You see here, there was no 1 here. Okay, so at zeros at the top, we had 1. So that one, we can represent it in the z inverse z transform format. So here 1 according to the inverse z transform will be what, x of n. Okay, because it's a 0 at the top, right, minus, this is what, z raised to the power minus 2, so this will be what, x of n minus 2. Okay, so that's the whole procedure of using the diagram. Okay, yes, but in case you still are confused about the conversion, you can go by the old route of writing it as a transfer function and multiplying it, and that one is done this way. Now in the transformation of this to the difference equation, remember that all along what we are doing is finding the transfer function of the filter. Okay, so it means that more or less what this is equivalent to is the same as y of z over x of z, because y over x is a transfer function. Okay, so what you can do is that you can imagine multiplying here by the denominator and down by the numerator, so that it becomes something like you have y of z times 1 plus 0.87796 z minus 2 is equal to 1 minus z minus 2 times what? X of z. Okay, now you can expand and find the inverse z transform. So when you expand, you realize I get y of z at 1 point plus 0.87796. It's too long. Let me just truncate it back. You know the raw value times y of z multiplying z minus 2 is equal to x of z minus x of z times z minus 2, right? The whole point I'm just trying to show you is that if you imagine it this way and find the inverse z transform, I mean, there is no way you can make the error of forgetting that here, when you compare it to the original standard format, here is supposed to be negative. Okay, like here is negative in the original standard format, so your answer, you should negate that one. Okay, but when you do it this way, then there is no need. Then you can go ahead. So when you find the z uh, inverse z transform, which you should be able to, you can realize that here is not multiplied by any form of z minus something. So here can just be y of n plus this is 0.8 whatever, but multiplied by z minus 2, right? So this becomes 0.87796 whatever times y of n minus 2, because it's multiplying by what? N minus 2, being equal to, then the left hand side you had x of n there, x of z there, so it just becomes x of n because it's not multiplied by any z minus anything, times x of z times what? Times z raised to the power minus 2. So that one will be, the z transform be what? X of n minus 2. Okay, then now you can make y of n the subject, right? And when you go through that procedure, you end up with this equation. So that's the whole step-by-step procedure. I believe there shouldn't be any question, but once there are questions, you can just still ask them in the comment section. I would try my best to review and, if possible, make another video to catch up. Thank you.